Good evening, students. So today we'll be seeing about Unit 4. So till now we have completed till Unit 3 and we'll start with Unit 4. So in Unit 4 we'll be discussing about visualization and data types of IIoT. So today's agenda we'll be discussing about front-end edge devices, and we'll be seeing about the enterprise data for Internet of Things, basically for industrial purposes, and we will be seeing about emerging descriptive data standards for IIoT. So first we will see about front-end edge devices. So if you consider front-end edge devices, they are the first point of contact. Okay, so between the physical world and the digital infrastructure, this is the first point of contact. This is the first point of contact in an edge computing system. So the thing is, these systems collect data from the sensors, machines, or other users, and it processes all the information locally. So this can be done via artificial intelligence and machine learning capabilities. So when you consider these types of systems, it can act or transmit insights to other systems by using cloud gateways or other actuators. So when you consider front-end edge devices, it usually refers to the computing or IoT devices deployed at the edge of a network close to where data is generated rather than sending everything to a centralized cloud or data center. So basically we'll discuss about the functions of front-end devices. So considering the data pre-processing, it can clean, filter or aggregate data, raw data before getting it, moving it into transmission. So considering the real-time decisions, it can enable fast responses without any cloud latency, and considering the protocol conversion, so it connects all the legacy devices, for example like modbus, profibus, and with other IoT protocols like MQTT, OPCUA, etc. So these protocols you have learned in unit 3, and based on the security enforcement, it handles local authentication, encryption, and anomaly detection. And considering the bandwidth optimization, it sends only the essential or summarized data to the cloud. So this is all about the front-end edge devices, where first point of contact is these devices where we can communicate with the outside physical world. So next we'll move on to front-end edge devices. So we'll see where it can be used. So front-end edge devices are endpoints or gateways, so that can perform data processing, filtering, and communication in various domains. For examples like factories, hospitals, homes, vehicles, etc. So it can send data to cloud or any other enterprise systems. So when you consider IoT sensors and actuators, it can be used for sensing temperature, humidity, pressure, vibration sensors, smart meters, smart thermostats, and other industrial actuators. And moving on to some front-end edge devices, we have edge gateways, where we'll be using routers or controllers that connect local IoT devices to the cloud, which can provide protocol translation. So, for example, you can consider Modbus and communication between other IoT protocols like MQTT. And moving on to some other applications like smart cameras or vision systems, it can perform real-time video analytics, so which can detect object detection, facial recognition, and it can be also locally used in other devices like wearables, mobile devices, and so on. So considering the wearables and mobile devices, we have smartwatches, health trackers, and we can use it along with AR and VR headsets. So it can also be used in industrial controllers. It can also be used in PLCs. We call it as programmable logic controllers, and along with distributed control systems. So when you consider distributed control systems, it can be combined with the edge intelligence autonomous systems. And we have self-driving cars, we have drones with onboard processing, and so on. So these two examples will come under autonomous systems. So when you move to the functionality and the use cases of these device types, we will some basic information about all these devices. So front-end edge devices are considered to be the smart layer. So it can access as the layer between the raw data sources, and it can act as the intermediate between the cloud and the raw data sources. So this technology which gives faster communication, and it is considered to be more efficient, and it can perform secure IoT or IIoT operations. So when you consider device type like smart sensors, yeah, we have some functionality like it can measure physical parameters and it can pre-process the data. So, for example, it can be used in air quality monitoring in smart cities. So, these are some device types, and we have other examples for front end edge devices. We have edge AI modules. So, it can run machine learning models locally for inference, and it can also have some example or some applications like real time anomaly detection in manufacturing can also be possible by using Edge AI modules. So next front-end devices, we have IoT gateways. So we have aggregate and translate data from multiple devices. So this can be used in hospital equipment integration and so on. And moving on to the next type, we have wearables and mobile devices. So which is used to capture user-centric data, and it can also perform localized analysis. So when you consider wearables and mobile devices, patient vitals tracking can be considered here, and it can be done in remote healthcare operation. So moving on to the next part, we have embedded controllers. So it can also interface with the machinery, and it can also execute control logic. So these types of controllers are used in industrial automation and robotics. So moving on to the next slide, we have some benefits of these front-end devices. So we'll see what are the advantages of using all these front-end edge devices. So considering it is very low, it has very low latency. So real-time responsiveness is highly achieved. So so by processing all these information, we can minimize delays which caused by distant cloud servers, and we have reduced cloud dependency. So here when you consider the systems become more resilient, and it is efficient for offloading tasks from centralized cloud infrastructure, and it can reduce bandwidth usage, and it can also reduce operational cost. So moving on to the next point, we have enhanced privacy and security. So data can stay in local. So sensitive data can remain on site or within trusted boundaries. So which can lower exposure risk, and it can improve compliance with data protection regulations. So next point is nothing but it is about the scalable deployment. So it supports massive IoT ecosystems by distributing processing loads, and it can enable seamless expansion without overwhelming centralized resources. So moving on to the next part, we have real-time examples of front-end edge devices. So we will be using these front-end edge devices in industry and manufacturing. So the purpose of this front-end edge systems can include real-time control of machinery, and it can process all the machinery parts. So for example, we can say it can control the robotic arms, where precise motion control is also possible, sequencing and safety interlocks. Everything is applicable by using these front-end devices. So these are some applications used in industry and in manufacturing. And again, moving on to the next part, we have conveyor belts. So it can also speed regulation. It can also detect object detection, sorting of logic. CNC machines can also be possible. So we have some advantages of using PLCs. where we can use it in harsh industrial equipments or in environments where we have deterministic timing for real-time operations. So it is easily programmable using ladder logic or function block diagrams. So it can also be used in industrial IoT gateways. So here we can specify the purpose of industrial IoT gateways as it can specify the bridge between field devices and higher level systems. And these IoT gateways can be used for sensor data acquisition, so which can involve vibration, temperature, pressure, etc. And it can also be used for local analytics. So for example, like running predictive maintenance algorithms at the edge and protocol translation, converting Modbus, OPC, UA, CAN, etc. And it can be used to specify in IP based formats. And you should also know why we use gateways. So it can reduce the latency by processing the data locally. So it can also minimize data, and it can also specify some cloud dependencies. So it which enables secure scalable integration of legacy systems into modern architectures. So when you move on to SCADA edge devices, we have decentralized control and monitoring of industrial purposes. So these types of edge devices can be used in real-time visualization. So operator dashboards can be used, alarms and trends which can use local control logic without needing constant cloud connectivity. So moving on to data logging and event handling. So the complaints and diagnostics are very much easy compared to other types. So we can also use these types of devices. And we'll move on to SCADA edge devices. So it can improve the resilience and it can uptime in case of network failures. So the advantage of using edge SCADA is nothing but it enhances security by limiting cloud exposure. So it supports hybrid architectures. Both it can be done local or via cloud for easy flexibility. So next we have real-time examples for front-end devices in healthcare. So when you consider healthcare, we have wearable health monitors. So for examples like Fitbit, Apple Watch, glucose monitors, which can track vitals in real time. So the purpose is to have continuous real-time tracking of psychological parameters. And we have some examples here. So we have seen that. So it can monitor the heart rate, which can monitor sleep patterns, which can also monitor the activity levels of individuals, oxygen saturation, and it can also detect anomalies like various anomalies. And it can also sync data with mobile apps or cloud platforms for trend analysis. So why do we use all these variables is it enables proactive health management, and it can detect early detection is also possible here. So it can really support remote patient monitoring, and telehealth communication can also be provided via these technologies. So it which can also empower individuals with personalized health insights. So, considering smart infusion pumps, we have automated precise drug delivery based on patient needs. So, this enables adjusting flow rates dynamically based on feedback. For example, we can say considering blood glucose monitoring levels, uh, pain scores, according to that, we'll be able to use all these variables. So these functions can prevent overdosing or underdosing through safety interlocks, so which can integrate with electronic health records for dosage tracking. And this can also be used to enhance the medication safety and treatment efficacy, and it reduces manual intervention and human error. So by using all these edge devices in healthcare, we can have great support in personalized therapy in critical care and chronic disease management. So, moving on to some portable diagnostic devices, we have on-the-go clinical assessments with edge intelligence. We have some examples like ECG monitors, which can detect cardiac abnormalities in real time, and there are some ultrasound wearables where we can have it in our hand, so we call it as handheld ultrasound, so which is used to visualize internal organs, often with AI assisted interpretation. So these types of devices can enable offline diagnostics, and it can support decision based on the input. So, uh, so moving on to some diagnostic capabilities, it can provide remote or resource limited settings. So it can also speed up clinical decision making without needing centralized infrastructure. So it can reduce the burden on hospitals or any other doctors by enabling point of care testing. So these are the major advantage of using front end devices in healthcare. So next we'll move on to some real-time examples which can be used in self-driving or transportation. So we can call that as automotive or transportation applications, where we can use electronic control units. So these electronic control units are represented as ECUs. So that can be used in self-driving cars. So the main purpose of using this electronic control units are nothing but it can perform real-time decision making for autonomous driving functions. So it can also fuse data from cameras, LiDAR, radar and GPS and so on. So where we can execute driving logic, where we can use driving logic. We can have lane keeping, obstacle avoidance can be performed, speed control can be controlled, and it can also respond to dynamic road conditions within milliseconds. So these can enable safe autonomous navigations without human input, which can also reduce accidents through predictive and reactive control. So when you consider these type of computational backbones like ADAS, we have advanced driver assistance systems. So these types of systems can be used in smart dash cams. The purpose is to specify continuous monitoring of road, and it can also perform driver behavior functions. So where we can detect objects, and we can use all these in traffic signs using AI. So next we have monitoring driver alertness, distraction and drowsiness, where we can record incidents for insurance, legal, and it can also be used for training purposes. So these type of systems can support safety and accountability, and it can also be used with real-time alerts and post-event analysis. So, when you consider all these domains, we can enable data-driven improvements in driver behavior, and it can also be adapted for fleet operations. So, when you consider the fleet management gateways, we can use all these management gateways with the help of edge-based optimization of vehicle, and these systems can provide tracking of vehicle location, fuel usage and engine health. So it can run diagnostics, and predictive maintenance can also be possible by using some algorithms which can be used locally, which can optimize routes based on traffic, weather and delivery schedules. So using all these things, we can reduce operational cost and downtime. It can also improve logistics efficiency and customer satisfaction. And it is very scalable, secure, and it can be used without cloud dependency. So next we are using all these edge devices at smart homes. So in smart homes we can use various devices like smart speakers, for example Alexa, Google Home, etc. So this process voice commands locally before sending it to cloud. So the purpose is to activate a control hub for home automation functions, where it can recognize and process voice commands locally, and it can use faster response control lights, and appliances, music, and routines can also be performed along with these types of smart speakers. So it can send refined queries to the cloud when it is needed. So it can also reduce latency and it can improve responsiveness. So moving on to some other basic smart home devices, it can enhance the privacy by limiting cloud exposure. The basic functionality is also enabled, and yeah, and in internet outrages it can also be used. And we have some intelligent climate control based on user behavior and environment functions. So these are all the devices which can be used in home automation. So whatever device we use, it can be optimized with the energy usage without relying on cloud connectivity support, and it provides a great support to real-time decision based on local conditions. And we often use all these types of devices to store all the information on cloud, and footage information can also be stored or in a stream to have an authorized access. So these all equipments can operate reliably even with limited bandwidth. So that's all about in home smart home. And next, moving on to telecom and networking. So 5G edge routers are used. So it's which is used to position at cell towers, and these devices deliver ultra low latency by processing the data, and the data is very closer to the user, enabling real-time responsiveness for applications like autonomous vehicles, remote surgery, and in it can also be used in AR VR. So when you go for content delivery edge servers, we have catch video or game data close to users. So it strategically located near end users, and these servers catch high bandwidth content. So for examples like video streams and online games, it can reduce load times and network congestion. So it also enhances user experience and scalability. So this is all about telecom and networking. So next we'll move on to OPC UA. So already I have told you about OPC UA. It's nothing but open platform communications unified architecture. So it provides a platform independent service oriented architecture. This open platform communication unified architecture is very robust, and it is designed for secure and dependable data exchange. So its service oriented architecture enables flexible integration across diverse systems, while it supports for semantic data modeling, makes it especially well suited for industrial Internet of Things applications. So when you consider OPC UA, it has a standard in manufacturing and process automation. It can also provide driving interoperability and intelligent connectivity across different industrial environments. So it is widely adopted in manufacturing and in process automation. So next we have emerging descriptive data standards for IIoT. So first we can have what is meant by asset administration cell. So you have to first understand what is meant by AAS. That is nothing but asset administration cell. So this is a foundational element of Germany's Industry 4.0 vision. So this asset administration cell, it serves as a digital twin for industrial assets, capturing and organizing all pertinent data and functionalities. So by providing a standard framework for asset representation, we use AAS facilities seamless with interoperability across diverse platforms and systems. This not only enhances the interoperability in Industry 4.0, but also has standardized digital representation of industrial assets where we can achieve standardized data structure. So, AAS provides a uniform format for describing assets. So, considering the machine's components or software, it can ensure that different systems can interpret and exchange data consistently. So moving on to the semantic clarity, it uses semantic identifiers and structured metadata, which allows systems to understand not just the data, but also it means it can give some critical or mission-to-mission communication, and automation can also be done with these particular standards. So next we have plug and play integration. So when you consider this, this can be done by encapsulating all relevant data and information, and it can function of an asset, and it can enable seamless integration across platforms and among vendors and life cycle stages. So which supports modular and scalable systems architecture. So this AAS supports cross-domain compatibility. So it supports not just within a single factory or enterprise, but also it supports supply chains and ecosystems, aligning with the broader industry 4.0 goals. So this is all about AAS. So next we'll have semantic web technologies where we have RDF, OWL and SPARQL. So we'll see one by one. So first moving on to RDF, it's considered to be resource description framework. So the using of RDF is nothing but it describes data as a subject predicate object triples and forming a graph structure. So we have some examples like sensor 123 which has a temperature of 75 degrees centigrade. So it can be adapted in IIoT where we can use model relationships between devices, sensors and events. So it can enable linking data across systems and from PLCs to cloud analytics. So powers platforms like Wikidata and Google Knowledge Graph, and we will be using all sort of information to create machine readable descriptions of industrial data. So next we have OWL. So we can say that as web ontology language. So the purpose of using web ontology language is nothing but it adds logic and semantics to RDF data through ontologies, and it has some capabilities like defining class hierarchies. Temperature sensor is a subclass of sensor where it can specify some constraints and inference rules, and it can be used in various industrial IoT which formulates domain knowledge. So it also supports reasoning engines for diagnostics, and it can be compliance with healthcare ontologies. And next we'll move on to SPARQL. So SPARQL protocol is nothing but we are representing both the protocols or both the web technologies. So we specify that as SPRQL protocol, and we have RDF query language, and it mainly uses queries RDF data like SQL for semantic graphs, and we have some features representing this particular web technology where we can have pattern matching, federated queries and semantic filtering. So it can return results as RDF graphs or tabular data. So we can use all these technologies in querying across distributed sensor networks, and it can support semantic search, and it can be used in real-time analytics in smart factories and cities. So we have so many benefits for RDF. So we have ontology, and for reasoning we have some content aware automation can also be done. And in SPRQL we have some query language. It can be done with semantic search, federated analytics and so on. So next we'll move on to emerging descriptive data standards for IIoT. So here we have some challenges to standardization. So we have some systems which can resist open standards to maintain market dominance. And based on the legacy systems, we have integrated old infrastructure with new semantic models, which can be very complex. So we can have some aligned terminologies, and we can use data semantics across industries. Considering the fermentation, we have sorry, considering the fragmentation, we have multiple standard bodies and consortia, which leads to overlapping efforts. So next we have digital twin integration, which can have descriptive standards, increasingly supports real-time synchronization with physical assets. So this can be done with edge to cloud semantics. Standards are evolving to describe data across distributed architectures. So we have some ISO IEC standards. So first standard we have ISO IEC 30141, so which can be used for architectures for IoT. And next standard we have IEC 21823, so which can be used for interoperability framework for IoT systems. So these standards provides foundational models for describing and integrating IIoT systems. So moving on to the next part, standards development organizations and industrial consortia. So this figure depicts the types of organizations placing in placing all these organizations in the horizontal axis, which corresponds to the phases of standards life cycle. So first we have users and vendors, so which can have a custom interface every time in every time, and it can interact with the other systems or components. So here the standards can make this explosion of interfaces manageable, and for suppliers this eliminates needless cost related to common capabilities instead of encouraging a focus on innovations and that can value all the capabilities. So the second is nothing but the information technology and the operational technology. So informational technology is represented as IT, and operational technology is represented as OT, which needs to work together where to achieve digital transformation of the enterprise. And this implies the OT can no longer deploy isolated islands of automation. So this can achieve the benefits of IIoT, where we have environments where we have connected components to enterprise systems and to perform communication with the various devices. Security and data norms can also be adopted. So this creates a competitive environment, and it can also support standards like international standards, regional standards, industry specific or function specific standards, which becomes a competitive for the organizations. And next, moving on to the standards which make employee skills portable, and it can perform actions across various divisions and companies, which benefits both the workforce and the companies that employ them by flattening the learning curve. So organizations must respond to these imperatives. Okay, so the strategy could be simple: to adopt and implement standards as they emerge. So, so in standardization, we have all the industry standards. So we have IEC, ISO, IEEE, ANSI, NIST, ETSI, one machine-to-machine communication, W3C, OSS, and so on. So compared with the specification part, we have OPC Foundation, Automation ML, VDMA with UMATI, Digital Twin Consortium, and so on. And we have open source foundations where we have Eclipse Foundation, Linux Foundation, and Apache. And moving on to some alliances, we have Labs Network Industry 4.0, Open Industry 4.0, Open Manufacturing Platform that we can represent as OMP. So this is all about the standards, and next we'll move on to standards development organizations. So here represent standards development organization as SDOs. So SDOs are nothing but they are entities responsible for creating, revising, and maintaining technical standards. So this SDOs play a vital critical role in shaping the technical framework that underpin products, services, and systems. So these things, these provide updation. We can also develop and manage standards that promote consistency. It can also provide safety, interoperability, and quality. While these standards are often voluntary, they can provide or they can become legally binding when adapted with regulatory authorities. So next we'll move on to standard development organization. So here we have some functions. So a standard is a repeatable, harmonized, agreed and documented way of doing something. So it is established by an accredited institution. So so the function is to develop and publish standards for materials, products, processes and services. So it can facilitate consensus among stakeholders including industry, government and consumers. So these standard provides interoperability across systems and technologies. It can also support regulatory compliance and industrial international trade, which can also provide safety and reliability in engineering, manufacturing, and service delivery. So this is all about the introduction part of SDOs. Next, we'll move on to defining standard strategy. So here we have some implementation and adaptation. First, we'll see where it is needed. So it helps enterprise evaluators to value the standards. So based on the benefits and risk, especially in relation to product roadmaps and intellectual property portfolios. So it reviews how companies can implement their chosen standards strategy. So it highlights how end users can tailor these strategies to suit their specific needs and roles within the IIoT ecosystem. So the purpose of this section is to allow enterprise to consider the range of strategies they might adopt with respect to standards. So we can review how the selected strategy can be implemented, and in a particular how a company may decide to contribute or it can actively used in standards, simply waiting for others to define them. So this is all about some information about defining a standard strategy. Next we'll move on to intellectual property versus standards. So as you all know, we'll have some basic idea about intellectual property and standards. So here we'll discuss in detail about these particular things. So so during the technology development, it is led by research groups, and we have some standards for adapting the innovation and technology. So the choice of mature standard compliant components or interfaces for the lower and intermediate layers can be provided, which can ensure components can be replaced by others, for example like plug and play compatible with the previous ones, etc. and so on. So the different parts of a system can readily interoperate or communicate with one another. So when the technology matures, customers discover the need for integration and for the interoperability, and they can migrate from one system to the other. So next we'll move on to drivers of a strategy choice. So when devising a standard strategy, we should consider all these following points. So end users of IIoT products or solutions can adopt the above strategy recommendations. So those end users organization should consider the following things. First, we have standards, which are a key to vendor independence, and it can reduce cost of integration. So applying IET standards to the OT organization will also result in enhanced and more secure deployed systems. So it can also create and maintain a list of standards that suppliers should comply with. So this requirement should be implemented in collaboration with the sourcing department. So it can be included in all the requests for proposals or quotations. Uh, Moving on to the next point, we can establish and measure a metric of success. So this can be done in terms of cost to integrate a non-standard products. We can consider training costs, the number of different protocols and interfaces, and so on. So this maintains the policy, the list of standards and the metrics. It will also propose which standards organization to join, develop and balancing the interest of the suppliers and so on. So moving on to the next part, we have executing the standard strategy. So it's a very important question. So here we will be focusing on four main parts. First, we have access the product portfolio. The second is implement a standard watch function. The third, we consider the defining the enterprise standards process. And the fourth, we call it as governance of standard activities. So in detail, we'll be seeing all these four topics. So this altogether we call it as executing the standards strategy. So first we'll be discussing about access the product portfolio, the first point. So when you consider this, we have some organizational building block inventory. So for example, an architectural building block constitutes one of the sources that can be used to generate a separate catalog for standards in which organization has a dependency or interest. And moving on to the specification, we have some building block. We can provide unique names for hardware, firmware, or software component. And typically, we can also have some bill of materials. And considering each particular component, we can have version number of the component. And next we have some specification. So reference to a document or documents describing the component specification can also be specified here. So we can also specify the source type. So we can include any one of these three. So commodity supply can be done with multiple suppliers whose products are interchangeable. So next we have the other supplies where we can use it for a specific supplier which is not interchangeable. And next we have open source, so software published by a community of developers. So next we have source. So name of the internal or external provider of this particular version of the product can be represented. The status of the thing can also be represented with these points. Legacy is no longer incorporated in new products. No applicable standards exist. So again we have standard complement not to be standardized, a non-standard no adequate standard is available, and next we have non-standard no adequate standard is available but development of a new standard is recommended. Moving on to the last part, standards compliance. So list of standards and their versions where the component is um, specified here. So next we'll move on to the second subheading where we have seen implementing a standard watch function. So when you consider a small companies, standard watch function may be used for a single person or by a small committee of people, which is done for a dedicated activity part time. So it helps to build a shopping list of potential areas of standardization because IIoT is a vast domain ranging from sensor communication to data analytics. So it can also provide divide and conquer. One can examine the various parts of IIC's industrial internet, where we have some architecture. We call it as IIC's industrial internet reference architecture. So it's very useful, and it can be used for desirable standards that can be filtered, that can be used for various attention. So these are kept evolving, and the designers need to be aware when the market requires an update and to a newer version, those few which the company should take an active role in creating. So these all things has to be considered to implement a standard watch function. So moving on to the third topic, we have defined the enterprise standards process. So here we have the flow of standard requirements and contributions. So first, the blue path, which denotes the standard requirements and contributions. We have some suppliers, new sources, standard organizations, product groups, standard watch and supply chain, etc. So the flow of the requirements and contributions between the parties are involved, and it can be represented by the graph. So in which the blue parts is considered to be the north and east parts represent the organizations, and it can provide the flow that can exist in an organization regardless whether they are formalized standards watch function. So moving on to the next part, south or west and center, so that are represented in brown ovals, that we can consider that as additional groups and interactions that result from adding this function. So organizational standards in this diagram can perform both formal standards and organizations and to the consortia. So their products should be specified here as standards include formal standards as well as other specifications. So organizations that can choose to follow the strategy of developing or contributing to the standards can be used with the diagram, which can verify the product groups, which is mainly used for supply chain department, and the standard watch group, which can implement all the necessary collaboration to execute the strategy. So we specifically include the supply chain department to highlight the role, so where it can play adding standards compliance to the requirements and so on. So we have some requests for proposals. So with that is represented as RFPs, and in this request for proposals, screening reserved received bids, it's considered, and it becomes an important factor in the implementation of the strategy. So next we'll move on to governance of standard activities. So this diagram shows a proactive standard strategy which results in multiple efforts throughout the company to watch, disseminate, document, adopt and adapt influence standards. So to avoid these duplication of efforts, a certain coordination and governance mechanism should be put in place. So for example, a supplier may participate in dozens of standard related activities. So it is important that a company to know which SDOs it has joined, under which membership agreements, and over what time period. So these can provide some information tracking the company's participation. Ensures the company can renew its participation in a timely manner, and then they can replace a delegate who has left the company, and disengage if the risk of sharing information with competitors, and it can exceed the advantages to be gained. So this is all about tracking. So when you move for IP protection, so failure to comply with the participation agreements, including the failures to disclose certain intellectual property rights, can be done. So when contributing technology to a standard, it results in a variety of legal risk. So, mature organizations participating in these standards have procedures in place, and we have IP aspect of each participation, and it can be performed with underlying IP strategies. So, development and implementation of a sound policy is essential and should be executed by the legacy department. So we have additional IP disclosure applications and so on. So where commitments and other tracking to ensure the commercial agreements and tracking should be accountable for these community of participants. So next we have community of practice. So where participants engaged in SDO activities are often dispersed throughout the company. So it can be done in a large organization. It can be done in a large organization, and it can be done in a specific work area or business groups. Building a company of building a company of practice of these participants help them share best practices, and it gives them a sense of identity. It allows direct cross pollination of efforts since the various standard areas often overlap, for example, like information exchange and security. So, moving on to the education and training, both business and legal resources should be allocated to educate the personal participation in SDOs in both the business strategy of the company and the IP protection standards. So, many larger companies have developed training programs to teach the company's engagement and approval policies or antitrust compliance. So, in some cases, advisory resources may be needed to participate in SDOs, governing bodies such as steering committees or legal working groups to execute effectively on the company's standards. So, since they have the greater visibility of the overall trust strategy, business should dive the engagements. So, next we have the policy and outreach. So, here where we can consider some organization allocate businesses technical and legal resources to work with the government and community affairs. So, doing all these things will help ensure that legislators are informed about the impact of their efforts and that public policy does not duplicate or contradict industry standards. So it can become unduly it can be a burden for the whole industry. So this is all about the governance of standard activities where we have tracking, IP protection, community of practice, education training, policy outreach, and so on. So next we have the conclusion part. So, adopting existing standards and participating in standards development. So, review should be done for the use of standards. So, whether it is in an own organization or in a different organization, review of standards has to be done, and it should be discussed with the leaders and they will be handling about the adoption of the strategies recommended in this document. So they will be providing the feedback on your own initiatives, and they will also be sharing the experiences in the use and development of standards to the IIC standards task group. So we call that group as STG. So volunteer can also suggest some standards. So these standard development organizations can engage with the IICs where they can suggest standard task group where opportunities are given with the other person's standard development organization you participate in, and it can be participated in the evolution of this document. So this is all about the conclusion part. So where we'll be providing all the information. So this is all about unit 4, the first part we have completed by today. So we'll continue the remaining parts in the parts in the later week. So thank you. Thanks for listening.